So good morning, everyone. And since there are people joining us from very different time zones, good afternoon, good evening as well. I'm Linus Huang, a postdoctoral fellow at the Society of Fellows in the Humanities. Welcome to the second to last lecture that's organized by the Society this semester. And today's lecture is also sponsored by the Philosophy Department and the AI and Humanities Lab. This talk will be around 60 minutes long. We have a lot of material, so we're giving Cameron a bit more time. It will be followed by a 10 minutes commentary and a short reply by the speaker. Then there will be about a 15 minutes Q&A before we end the event formally. However, if there are more questions, Cameron has agreed to stay a bit longer for another 30 minutes. And before we get started, I would like to inform everyone that this lecture and the Q&A will be recorded, and it will also be broadcast on the Society's channel. And I've just posted the instruction for Q&A and the handout for this talk in the chat. So you'll know what to do. Okay. So our speaker today is Professor Cameron Buckner from the University of Houston. Cameron is Associate Professor in the Department of Philosophy, and his research interests lie at the intersection of philosophy of mind and philosophy of science. Drawing on these two perspectives, he has worked on issues related to cognitions, broadly construed, including human, animal, and artificial intelligence. His 2017 articles, Rational Inference, The Lowest Bounds, won the American Philosophical Association's Article Prize. And he's now working on a book that's currently under contract with Oxford University Press called Deeply Rational Machines, a philosophical exploration of deep neural network-based AI. So today we'll be able to take a peek into this very exciting project. So please join me to welcome Professor Cameron Buckner, who will tell us why ideational preparation is all you need.
Okay, thank you for the invitation, and thank you for the attention of everyone in the audience. I'm really looking forward to Amit's comments too. Let me see if I can go ahead and share my screen correctly. So I wanted to share this one, and then let me see if I can get my slides going. Okay, so do you see the right slides now, Linus?
Yeah.
Okay, good. So you don't see my comments. All right. So as Linus mentioned, I'm writing a book right now on support from the National Science Foundation here, and sort of the general idea of the book is to use empiricist philosophy of mind to help us understand what's going on in deep neural network-based artificial intelligence, which has made a series of transformative breakthroughs in the last 5 or 10 years, even huge things happening in even the last month, if you've been following the news. And I'm focusing mostly on philosophers from the Western analytic tradition, like Hume and Locke, and a little bit older Aristotle, Ibn Sina, and William James is the one we're going to focus on today. So today I'm going to give you, I'm going to focus in on one particular chapter that happens a little bit later in the book. But I'm going to try to give you a brief pitch for the whole project, like why empiricist philosophy of mind might be relevant to understanding and maybe even guiding the future development of deep learning, that is deep neural network-based artificial intelligence. So the plan of the talk is, first I'm going to sort of give you the general pitch of how the old debate between rationalism and empiricism in the kind of Western tradition is being applied to this debate in deep neural network-based AI today, and what the stakes of that debate are in philosophy and in engineering. And I'll focus on some topics that I've published on a bit more in the past in some of my papers that some of you might have seen, in particular on a type of architecture called deep convolutional neural networks, which are regarded as maybe the best models of human vision or visual processing that we have today. And then I'll give some of the generic criticisms from the rationalist or classical AI camp of the achievements of the deep neural network-based artificial intelligence. And then I'll talk about how attention might solve some of the problems, both that we already know these networks face, and some that might be yet on the horizon, that as these networks get more complex and more powerful, we should anticipate and develop countermeasures before before the problems are really causing big issues. And then I'll talk about, after I introduce in particular an approach to attention that's found in the work of William James, I will talk about how attention is already being modeled in a variety of ways in deep neural network architectures, indeed some of the ones that are behind these kind of headline grabbing achievements that you might have heard about, especially with transformers. And so the title of my talk is kind of a play on the most famous transformer paper, which says attention is all you need. And ideational preparation is William James' approach to attention. So I'm going to suggest that a more Jamesian approach to attention in deep learning might deliver even more impressive results than we've seen so far. So, unless you've been living under a rock the last 5 or 10 years, you've probably heard about this headline grabbing achievement by DeepMind's AlphaGo system, which beat a human grandmaster in the ancient Chinese board game of Go, which was regarded for a long time, even after Deep Blue beat Garry Kasparov in chess in the 90s, as something that AI would never be able to solve, right? Because there are so many possible moves in a game of Go, right? So, there's 250 to 350 possible places you could place a stone at each turn. And so the space of possibilities that you would have to search if you were going to try to search through the game by brute force, it grows exponentially at a huge rate. So there are more possible board configurations that you would have to consider to solve the game of Go through brute force computation than there are atoms in the universe. So the thought was, it doesn't matter how much computation you throw at it. You'll never be able to solve it without, in particular, something like intuitive intelligence. So if you ask human Go players how they play, they often explain their strategies in terms of abstractions like balance or stability that are difficult to put in the form of an explicit algorithm. But nevertheless, AlphaGo was able to defeat Lee Sedol pretty handily. And so this led a lot of people to think that, maybe there was something really new in this approach to artificial intelligence. And AlphaGo was in fact based on a deep neural network, a deep artificial neural network that was broadly inspired by the structure of the human brain, right? The idea being that the brain is a large network of neurons that are all communicating with one another in parallel. And that's the structure that's kind of under the hood in AlphaGo, modeled at some level of abstraction. Now, what's interesting to me for philosophical purposes is that even in the first sentence of the Nature paper, where the DeepMind team published their AlphaGo system and explained it, they mention, actually this is AlphaZero, a follow-up to AlphaGo, but they mention this tabula rasa algorithm. And this phrase here is directly referencing the history of empiricist philosophy, descending from Aristotle and continuing down through Locke and Hume. So, they're drawing inspiration, it seems like, and using this tradition of empiricists thinking about the mind to justify and explain their results, even in the first sentence of the abstract. And the critics of this achievement of AlphaGo, the people who want to say like, no, let's not get sucked into the hype. This still isn't really intelligence in the way you might think it is. Like Gary Marcus also referenced this classic debate between empiricists and nativists that goes all the way back in some form to Plato and Aristotle. So as a philosopher, you might worry, are you sort of like foisting this philosophical debate on the engineering? And I want to say, no, they're doing it themselves, right? They were doing this before I came onto the scene. But I do want to suggest that maybe the wrong lessons are being imported from the empiricist, nativist, rationalist debate, or maybe we need to have a more subtle understanding of the philosophical positions to offer the most useful advice and guidance to engineering here. And a lot of my talk will be about that. Now, there's lots of ways to cut the pie when you're trying to understand what is this huge debate that's played out in some form in thousands of years in different traditions amount to. There's lots of different ways to say, to try to decide what the central issue is. I just want to be clear from the beginning, I'm focusing on the origins of the mind's knowledge. Okay, I think that's what the tabula rasa language references. So in particular, the question is, what's the origin of abstract knowledge? For example, the abstract idea of a triangle is one a lot of people talked about in the history. In particular, is it innate? That's the more rationalist or nativist approach. Plato famously had this story about unpacking knowledge from before we were born into a human body through this story of reincarnation when we're exposed to the pure forms of knowledge. And Aristotle said, no, we need to learn all these abstractions from sensory experience, that is information that we get through our perceptual senses like sight and hearing and touch and so on. So the empiricist says abstract knowledge comes from the senses, and the rationalist or nativist says we're more unpacking some innate ideas that come from various sources. Today, the nativist, of course, focuses more on evolution than stories about reincarnation. But it's the same basic opposition between knowledge coming from an innate endowment in the mind or being extracted from sensory information that we get through sight and hearing and so on. So, you know, there's this opposition that's played out in nearly every academic discipline in one form or another. You can find some form of empiricist and rationalist debate. And you might think, is this really the right thing for engineering to focus on if they have primarily practical goals, right? They just want to make the most successful system. So why care about this sort of timeless philosophical question that looks like, you know, even though we've been fighting about it for thousands of years, you might worry it didn't make a lot of progress. But I actually think there's a possibility here for a mutually beneficial meeting of traditions here, where what we can do is treat this philosophical riddle now as a empirical question that can be resolved with engineering methods. So in particular, now that AI has finally reached the point of sophistication where we can actually build some of these ideas into artificial systems, the idea is that we can just build some robots according to rationalist principles, that is building in a lot of rich innate knowledge, and build some other robots according to empiricist principles, that is with very powerful learning systems where they learn all the abstract knowledge from experience. And we just see which set of robots is more successful or more human-like, right? And that can both help us arbitrate this classic philosophical dispute, while at the same time the engineers can take inspiration, right? Like sort of get problem sets and challenges from problems that were proposed in the history of this great debate. So I think there's a possibility for a nice mutually beneficial meetup between philosophy and engineering. And I'm not the first to say this, right? So like Russell and Norvig it's as close as there is to a Bible in artificial intelligence. In the first couple of chapters, they reference this way of understanding the dispute and suggest that, you know, Aristotle, you can actually unpack some good algorithms for rational decision-making in artificial systems from things Aristotle said, and like the Nicomachean Ethics and so on. So there's uptake even in the AI community for this importation of philosophical tradition. There's another good blog post from Judea Pearl, maybe the most influential living computer scientist, that draws a link between recent machine learning developments and what he calls radical empiricism. And one of the most influential critical articles by Lake, Ullman, Tenenbaum, and Gershman also references the empiricism rationalism debate. This is in behavioral and brain sciences. And they say in particular that Alan Turing was motivated by this empiricist way of thinking when he suggested that we should view the artificial machine as being like a child's mind with rather little mechanism and lots of blank sheets, and the hope that by responding to rewards and punishments, it could acquire abstract knowledge. And this is the part I really want to draw attention to. They then quickly link this empiricist view to behaviorism in psychology in the 20th century, especially dominant in American psychology. These are figures like Watson and B.F. Skinner, if you followed the history of psychology in the American tradition there. And they say cognitive science repudiated this oversimplified behaviorist view, which came to play a role in early AI, and that repudiation came to play a role in early AI research. This is a very common way of setting up the historical linkage here, and I think it's quite problematic. So this is something that I want to draw attention to. Something you see again and again from nativists like Marcus and Steven Pinker and so on, is they say empiricism, therefore psychological behaviorism like Skinner, therefore super wrong, like Chomsky's supposed to have shown us that this is all hopeless and wrong. So let's not go down that confused and hopeless path again. I think that's all very problematic set of connections for reasons I'll shortly explain. Now I want to stop and say, look, it's not behaviorism. So what kind of empiricism should be attributed to recent deep learning achievements, right? Steven Pinker, who draws the linkage I just mentioned to psychological behaviorism, kind of makes fun of it as a hopeless view, saying that, like, look, if it's really a blank slate, there's no innate structure whatsoever, it's not going to learn from any amount of experience. It's like throwing experience at a rock. right? It's never going to learn anything, no matter how much experience you throw at it. So there has to be some innate structure. Gary Marcus, furthering this critique, even puts a little bit more formal attire on it. He says, think of cognition as defined over 4 variables, A, R, K, and E, where A is innate algorithms, R is innate representational formats, K is innate knowledge, and E is experience. And he says a true blank slate would set K and R to 0, A in some extremely minimal value, and leave the rest to experience. And then he says this is the view that Locke articulated when he said all ideas come from sensation or reflection. I think there's a very problematic inference and reading of Locke going on here very quickly, where the idea is there's just no innate structure whatsoever in the mind if you're an empiricist. I think that's wrong. I think empiricists all along, all the way back to Locke, even all the way back to Aristotle, they were offering a thesis about the origins of the mind's representations or concepts, but they could have all kinds of other domain general innate structure in place to get that. In particular, they can have faculties, which I'll talk about shortly. That's the piece that's really missing from this Marcus way of setting up the debate. So I think this is essentially a straw man, and we shouldn't set up the debate in this way because it's not useful to beat up a straw man. It doesn't provide useful guidance to AI. In particular, this is a place you could look for a lot of citations about the faculties. So the idea is, Hume, Locke, all the other major empiricists, Aristotle for sure, they all knew that the mind had this kind of rich cognitive architecture. And they thought that essential to explaining how the mind extracts abstraction from experience. So rather than it being like a rock and there's no innate structure whatsoever, if you look at how Hume and Locke think we get abstract ideas from experience, they're constantly referencing the imagination, memory, perceptual abstraction, reflection, the passions, and these are all innate. They don't say that these things all have to be learned, right? So this is, I think, what's actually bolstering a lot of the recent achievements in deep learning, and it's the right way to understand what the empiricist gets to start with when they're entering into this kind of competition with the nativists about how we get abstract knowledge. So why is the history of philosophy important here? This is me kind of summarizing. The question of empiricism versus rationalism is seen by the major players in this debate as having crucial consequences for engineering methodology. In particular, should we build high-level representations into the system from the beginning, or should it be deriving it all from experience? And but this connection is not being drawn in the most productive way. Deep learning, I think, channels actually the historical empiricists, not the psychological behaviorists, like Watson and Skinner. So Hume and Locke, yes. Watson, Skinner, no. That's not what's happening. And machine learning can fill in some philosophical gaps left by the historical empiricists. So when they're talking about these faculties, in particular Hume, he'll often say, like, look, the imagination does this, or the memory does this, but I don't have the slightest idea how, and I'm not even going to try to tell you. There's something sort of admirable about that. He wants to sort of insist that this job gets done, but he has no idea how it happens. And there's a possibility now that, if we could offer a machine learning model built according to empiricist principles that could actually perform these operations, we might be like filling in this ellipsis that Hume gets beat up about by his critics for hundreds of years for not explaining how this works. We might finally be able to cash in that promissory note and explain how the faculties might do these operations that the empiricist needs them to do in order to get abstract knowledge from experience. And moreover, engineers might continue to mine gems from the history of philosophy, especially for more general cognitive architecture. In particular, I think that the engineers have not yet had a chance to think about how all the bits and pieces of the systems they've been building might fit together into a comprehensive approach to the mind. We're only now seeing some sort of papers in deep learning that are trying to tackle that problem. Whereas thinking about how everything hangs together is something that a lot of the major empiricist philosophers, wrote entire books about, right? How does this all fit together into a kind of systematic approach to the rational mind? There might still be a lot of inspiration that the engineers could take here. Okay, so that's the pitch why philosophy could even be relevant here. Now let's talk about maybe the most well-established success case so far of deep learning as a model of the human mind, or of rational capacities on an empiricist picture. And that's deep convolutional neural networks as models of human vision. Now, there's not time for me to go through all the nitty-gritty activation functions and so on of how this works. But the basic idea is you have a very deeply layered neural network. where each layer is got a bunch of nodes in it that are performing simple activation functions that are simulating the firings of neurons at some levels of abstraction. And you throw high dimensional input, like in this case, a picture of a cute kitten, at the input layer of this network, and they do their operations and they kind of iteratively transform the signal that they get at each layer. And so the signal gets hierarchically transformed as it goes up the layers, and there can be lots and lots of layers in one of these deep neural networks. That's the sense in which they're deep compared to earlier networks, is the number of layers of nodes that are processing the signal in between input and output. And then finally, the highly processed signal gets passed to an output layer that might, and if this is an image classifying network, be trained to assign a label to the task. So in this case, it might say, well, in virtue of this transformed signal, I think that this picture is likeliest to be a cat. And these networks are, in many cases, as good or better than average humans at labeling images that they get from the network. They're trained on massive amounts of labeled data. So from data sets like ImageNet, where you have, I think it's something like 20 million images or 14 million images annotated by over 20,000 labels. It takes a lot of data, so that's one concern that you might have about these, but they get pretty good at doing it. Now, I've written a lot about this in the past. I'm not going to fully reprise all those details. You can read a couple of my papers if you want to get into that. But this structure was roughly inspired by neuroanatomical study of mammalian cortex. So in particular, there's this story about the ventral stream processing being layered, where the visual processing starts in V1 and goes to V2 and V4 and V5, and then to posterior inferotemporal and anterior inferotemporal areas. And if you look at the what those brain areas seem to be responding to in input, it looks like they're responding in the beginning of very, very specific and localized features, and then getting more and more abstract features as you move up the hierarchy. Some of the neuroscience in the history here, in particular discoveries by Hubel and Wiesel, found that there were two different types of cells, where it looked like one was responding to a feature in a particular location in a particular presentation. And then another type of cell that they called complex cells was aggregating across several simple cells to make, one simple cell might detect a line like this, and another like this, and another like this. And then the complex cell takes input from all those and aggregates across them to make the detection of like a line in some orientation about this location. So it's a little bit more tolerant to nuisance variation in terms of the pose and other ways in which a line could, lines could differ from one another. So if you think about to where we started, this is directly relevant, this ability to control for nuisance variation, to like an abstract ability to detect triangles, right? Because the reason that's a hard problem is that triangles can be of different shapes, they can be of different orientations, they can be of different sizes in the visual field. They can have different number of angles, right? These are all forms of nuisance variation that the brain seems to solve by adding a layered deep hierarchy. And that's in particular the aspects of the ventral stream that we try to replicate in these artificial convolutional neural networks. That probably explains why they're also good at solving this type of task. So from the beginning, this was kind of inspired by neuroanatomy, and that might be why it works. And in fact, if you try to understand the types of features that are extracted at different layers of the neural network, it seems like they're starting at the early layers at more specific features like contrasts and shadings in particular locations, and then building slightly more abstract features. Like if this is a face detecting network, you might start to get things that look like eyes and noses and mouths, and then building more like whole types of faces at the later layers. So it broadly seems to correspond that there's like a layer of abstraction happening as you go up to the network. There's also interesting empirical evidence that this is doing something like what the brain is doing. So now one thing we can do is implant electrophysiology arrays in live monkey brains and have them solve the same types of image labeling tasks that the deep neural networks are doing. And we can compare the neural firing patterns, this is in the live monkey brain, to activation patterns in correspondingly deep layers of an artificial neural network trained to do the same task. And we find, this is work by DiCarlo and Yeomans at MIT, we find that the same types of features are about as easy or hard to extract at the same levels of the hierarchy. So more specific features are more available at earlier layers, and more abstract features are more available at later layers. in both the live monkey brain and in the deep neural network. And the important part about this is that these networks were not trained to do this, right? They were only trained to solve the input-output task. So the fact that there's appears to be some kind of correspondence between intermediate representations looks like interesting confirmatory evidence that they're solving the problem in the same sort of way. I won't say much more about this, but if you want to further review, Grace Lindsay, whose work I admire a lot, has a great review paper that is from last year. That's a little bit more up to date than anything I've written. Okay, so I think this is actually useful in understanding what the basic tenet of empiricism should be here, right? So you might worry, if Marcus and Pinker are getting it wrong or reading empiricism as a kind of straw man, what's a more subtle or charitable way to read it? I think a lot of the rationalists are reading a very constrained version of empiricism out of some of the standard mantras that are used to characterize the view. Fodor in particular, Jerry Fodor, makes a lot out of Hume's copy principle, which says all our simple ideas in their first appearance are derived from simple sensory impressions which are correspondent to them and which they exactly represent. And Fodor reads this as really restricting what the empiricist mind could do. It's like all it can do is sort of like copy sensory impressions. And if that's all you can do, then it looks like you can only build more complex mental representations by kind of just like juxtaposing or concatenating simple sensory impressions that you get. And it seems like the mind does more than that. But there's evidence in all the empiricists that they thought the mind was more powerful than just like sticking together sensory impressions, like juxtaposing colors and shapes or juxtaposing sounds and stuff. So Hume, for example, says, nothing is more free than the imagination of man. And though it cannot exceed the original stock of ideas furnished by the internal and external senses, it has unlimited power of mixing, compounding, separating, and dividing these ideas in all the variety of fiction and vision. So it looks like it's much more powerful than simply just sticking ideas together that it gets from the senses. Tomas Demeter has a nice paper here rebutting kind of this rationalist constraint on empiricist thinking. And he thinks that a lot of people read Hume as trying to be like the Newton of the mind, to try to make psychology more empirically respectable, more scientific, by making it more like mental physics, right? Like ideas are like physical particles interacting with one another. He suggests that that Hume was actually operating on a picture more like mental chemistry, where you can combine different ideas, so the faculties in particular. Hume's talking about the imagination here, right? Something that the straw man reading should not be allowed to access if you're believing, Pinker and Marcus and the other rationalists. But it's more like mental chemistry, where the idea is you can combine two elements and they make a compound. And the compound has properties that are more than the sum of its parts, right? It's not just additive. They might be able to kind of blend in novel and interesting ways. And you see the effects of this, I think, in a lot of recent deep learning achievements. So I suggest the basic tenet, and I think this is really just clarifying what Hume meant all along, but I call it the transformation principle. And this is that the mind's simple concepts or conceptions are derived from systematic domain general transformations of sensory impressions. So like anything that a deep neural, the idea is you have to get the raw materials for these transformation operations from the senses. But the faculties can implement all kinds of specialized transformation operations, as long as they're just transformation and doing sort of domain general transformations on the raw materials that they get from the senses. All of that is fair game for the empiricist picture. And in fact, I think that's what a lot of the neural network architectures do that are doing all these cool achievements that we read about in the news and in the prestige publications like Science and Nature, is they're finding new transformation operations that can produce like novel and interesting and useful compounds by blending together in novel ways the information that they get from their training data. Okay. Now, you might know, all of you, that there are some sort of generic criticisms of deep learning that are supposed to like limit its potential to just keep exploding the way it has been over the last 10 years. So you might worry that it requires huge amounts of training data. You might worry that its behavior is brittle or vulnerable to adversarial examples. I can come back to adversarial examples if people want to hear more about that. I love talking about this. I can give a whole talk on it, so I'm not going to lose 15 minutes to my adversarial example rant right now. You might worry that they're big and opaque, that like they're so big and complex, they have billions of parameters, you can't understand what they're doing. You might worry that their behavior doesn't transfer or generalize as well to novel problems, or you might worry that they have trouble distinguishing correlation from causation. I've written about all of these criticisms, so you might look at my BJPS paper here if you want to see my take on all of them. I think a lot of them are overplayed. I worry a little bit more about the last one than the others, but we can talk more about that in the Q&A if anybody wants. The important point for the stuff I want to talk about in the latter half of the talk is that it does look like deep convolutional neural networks at least can learn significant abstractions from experience, more than the rationalists ever thought they would, by modeling some abstract structure of the primate brain. And you might say, well, is that enough for intelligence or cognition or rationality? We want to say no, right? I mean, even though this is cool and it's a huge breakthrough, like for cognition or rational decision making, you say we still need more than just like the ability to label cats, right, in images. We want some greater degree of flexibility or greater degree of efficiency or display of insight or creativity and control. That is where the faculty of attention is going to come in. That's what I'm going to talk about for the rest of the half of the talk. Just to give you a quick pitch of the book project, each chapter talks about a faculty, and it has a kind of philosopher of the week format, where I pick one particular philosopher who gave, to my mind, a particularly interesting and useful take on that faculty, and then I link it to some recent developments in deep learning. So I talk about Locke on visual abstraction, and then compare that to DCNNs, Hume on the imagination, and I compare that in particular to GANs, Ibn Sina on memory, and there's a couple architectures there. And today I'm going to talk about William James on attention, and in particular transformers. And then I talk about sympathy to get more like moral and social decision making, and I like the work of Sophie de Grouch there. Can talk more about that in Q&A if anybody's curious. But that's the structure of the whole book. The remainder of the talk is going to be just on chapter 6. I call this a new empiricist dogma, where dogma stands for domain general modular architecture. You have to have a good acronym if you want the computer scientist to take you seriously. And it's also kind of a tongue-in-cheek reference to Quine, right? The two dogmas of empiricism that he got from logical positivism. But I also want it to be tongue-in-cheek in the sense that we should only keep the dogma as long as it is empirically useful, right? As long as it is sort of bolstered by data. We shouldn't actually become dogmatic about it in the sense that we just keep pushing it in the way that maybe the behaviorists in psychology did long after their research program was not as plausible anymore. I'm going to jump ahead. So the key idea here is to address those worries that we had about those generic objections that we had about deep learning. We're going to appeal to the faculties. That's the thing that like the straw man reading of empiricism doesn't have, but I think every major empiricist had, and in fact, deep learning has a lot of now. So perceptual abstraction is going to allow us to abstract categories from complex experience. I already talked about that. Memory is going to allow us to replay successful experience trajectories for offline learning. That's going to help with sample efficiency in particular. Imagination will allow us to compose novel ideas and experiences and choose on the basis of simulated experiences of future outcomes, and even engage in offline simulated learning. And I'm not going to talk about that anymore in this talk. But you know, if you want to talk in the Q&A, these are chapters that have already happened at the point of the attention chapter in the book. They set up the attention chapter though, because the idea is as we add more and more faculty modules, our cognitive architecture is getting more and more complicated, right? We have more semi-independent modules with their own distinctive computational operations, and they might start to clash with one another, right? So, and this is a kind of problem that all the major empiricist philosophers worried a lot about. So like Hume and Locke worried all the time about people confusing imagination and memory, or imagination and perceptual experience, and sort of getting like lost in their reveries and making all these strange mistakes. And Locke even analyzed a lot of mental illnesses along these lines as confusions between faculties sort of like not coordinated in the right way for rational cognitive architecture. So I summarize these problems under the heading of what I call the control problem, or that other people have also called the kind of control problem. Is the idea is that we get more and more semi-independent faculties competing for shared resources or control over action. we need some way to coordinate their operations and arbitrate conflicts. And attention has long been considered sort of like the faculty for this job. The idea being that if you sort of focus on just the right aspects, you can figure out how to get the faculties working together in the right way. So here's some examples of control problems that might pop up as our faculty architecture gets more complex. How can we switch between modes, like from active perceptual monitoring to memory recall to imaginative simulation to daydreaming? How could we select amongst different sources of ideas? I already said how the early modern philosophers worried a lot about that. Even within a single faculty, how can we decide which abstract comparisons are relevant? So Berkeley has these examples of like, if we have these two spheres, we could compare them in terms of their color, their shape, their location, their size. There's like an infinite number of different ways you can compare any two objects. And which abstractions are relevant, right? Like Berkeley's theory of abstraction depended a lot on the idea that, well, you just attend to a single dimension of similarity. And that's what allows you to extract the information you need from the comparison of the two objects. So attention is useful there, and deciding sort of like which aspects of a perception to attend to. And also, how can we be flexible in the face of environmental interference? So you might imagine like you want a robot to do some job, but you also want it to be like looking out for dangers or interference, right? That's a kind of balancing act too, right? In some sense, it needs to keep monitoring the background for stuff that might cause problems, but you also want to keep it with an ability to reorient to the goal or the previous computation that it was performing. That might be a job for attention too. So it looks like it needs to be a kind of jack of all trades faculty if it's going to solve a lot of these problems. James says some famous things about attention. A lot of psychologists who work on attention always start with this quote from James. He says, "Everyone knows what attention is. It's the taking possession by the mind in a clear and vivid form of one out of what seems several simultaneously possible objects or trains of thought." Despite the fact that James seems to think attention is pretty easy to understand, there have been a couple recent review papers that survey the disorder in the psychology of attention in particular. So this famous review paper by Hummel says, "We argue that the overuse and popularity of this statement in cognitive research has been detrimental to progress, and that in fact nobody knows what attention is, because there's so many different theories out there and they all seem to disagree about basic things about attention." Another way you might try to play up this worry that there couldn't be a coherent take on the faculty is that so many different roles or effects are ascribed to it. So it's supposed to be something that enhances processing. Like if you're attending, you should be processing something better by, for example, increasing detail or accuracy or precision, vivacity, or ability to detect errors or discrepancies. It might be considered a necessary condition for conscious awareness, right? A lot of people think that if you're not attending to something, you can't be consciously aware of it. It can also cause diminished performance when taxed. So a lot of experimental designs will give you attentional load, they call it, right? Like tell you to do some other task and then see if you notice something else. And we notice that processing is diminished when there's attentional load. It can be affected by a variety of brain injuries or drug interventions, by various psychological pathologies like OCD. It might also help distinguish two different systems of thinking. The idea being that system 2 is the one that involves the application of attention, if you're familiar with this distinction from like Kahneman, Tversky, and so on. And so the worry is like, could one thing really do all these things? It looks like attention is solving all problems for all different types of people. Could it really be the case? I'll suggest some optimism here later on, but I want to amp up the pessimism so it looks more impressive when if anybody leaves remotely optimistic at the end. There have been a variety of sort of big programs to study attention in psychology in the 20th century. So they all sort of agree that attention is a form of selection of what to process. This all started with Broadbent's filtering theory, you might think. The idea being that there are constraints on how to pass information around a computational system like the brain or an artificial computer system. And so you have to select what gets to pass through this limited channel of communication. As parallel architectures like neural networks became more popular in the 80s, this started to look like less of a problem. There were like not as many bottlenecks if you can process, hundreds or thousands of things simultaneously. And there the problem was actually, how do you bring it all back together into a coherent solution to problems? And so Anne Treisman developed feature integration theory, the idea being that attention was a way that you bring together or integrate the various forms of processing in different modules in a system. There are also agency-focused theories, this especially in the work of Wayne Wu recently, and cognitive unison theory is a kind of deflationary theory, the idea being that there's no special faculty of attention, it's just kind of whatever is the winner of a winner-take-all competition between different modules competing for resources is just, that's what we say we're attending to, but there's not like a separate thing doing the attending. So there's lots of different theories out there. And again, you might worry whether they're all talking about the same thing or one thing could explain all the data that they're reviewing. Let's jump back to James now, and then I'll try to motivate the optimistic view that there actually could be one thing here. In fact, one thing that could be modeled in interesting ways by a deep learning architecture. So returning to this quote, he says, it implies withdrawal from some things in order to deal effectively with others, a condition which has a real opposite in the confused, dazed, scatterbrained state, which the French call distraction and Zerstreuheit in German, right? In James' views, it's not an idea creation system or storage system like perception, memory, or imagination, but nevertheless, it bears an intimate connection to these other faculties. James offers a bunch of different sort of taxonomic cuts, ways to think about attention and its operations. It can be sensorial or intellectual, that is, you can attend to sensory experiences, or you can attend to ideas like memories or imaginings. It can be immediate or derived. Immediate is kind of like, it happens more or less before learning or without extra learning. And derived means it's on the basis of kind of a learned effect. And it can be passive or voluntary, right? So it can be sort of like against your will, like a loud sound grabs your attention, even if you're trying to focus on writing your paper or whatever, right? Or it can be voluntary, like you're trying really hard to focus on something and succeeding or not. He also has this interesting comment that volition is nothing but attention. So for James, it's tied to action and the will in this very rich way. The idea that there's nothing that there is to try to do something voluntarily except to attend to doing it really hard. He has all these nice examples of all the different combinations of these cuts. So, like passive, immediate sensorial attention is like the loud noise grabbing your attention sort of automatically without you attempting to attend to it or being aware of it. You can also have immediate passive intellectual attention. I love some of these examples like derived, so it's learned. It's passive, so it happens kind of quickly and automatically, and it's intellectual. So he has, there's this famous anecdote of Archimedes, a mathematician, who was so absorbed in his geometrical meditation that he was first aware of the storming of Syracuse by his own death wound. He supposedly told him, like, don't disturb my circles that I was drawing, right, or whatever. So, it's a fun chapter to read, and I urge everybody to read it themselves. But again, you might look at all this and be like, gosh, James thinks there's one thing here. How could this possibly all be one thing? Jesse Prinz tries to confront this challenge directly in making sense of James' views and suggests, yeah, there really is one thing here. And he's sort of just summarizing and rephrasing things that James says, but he does it in a particularly nice way. So I also recommend this chapter by Jesse that came out last year, if you want to make sense of this stuff. So the idea is there's two basic expressions of attention in James to bring together all of these pieces. And he calls them organic adjustment and ideational preparation. Organic adjustment is the easy one. That's just the movement or change in the sensory organs themselves to accommodate the thing that they're attending to. So that's like moving your eyes around or moving your head or squinting or pupil dilation, right? To sort of like better focus on a particular input. So I'm not going to talk more about that now. That's hopefully a pretty straightforward one. Ideational preparation is the interesting and tricky one, though, right? He says this is the anticipatory preparation from within the ideational centers concerned with the object to which attention is paid. So this is much more than just like a mental spotlight. And he even says it's explicitly a modification of the faculty of imagination. It's attempting to sort of guess what the spotlight will find before it's shined there. So he talks about this example of trying to attend to something in peripheral vision without moving your eyes. So, keep your eyes focused, put something in your peripheral vision and attempt to attend to it, right? He says that's doing nothing more than the effort to form as clear an idea as is possible of what is there portrayed, an imaginary duplicate of the object in the mind, which shall stand ready to receive the outward impression as if in a matrix. Now, if you're a philosopher of psychology or a psychologist or even computer scientist who has been keeping up with other developments recently in these areas, you might know that sort of predictive approaches to the mind have also been kind of popular recently. And this looks an awful lot like a kind of predictive theory of attention. The idea being that all it is to attend to something is to try to form a forward model of the low-level sensory impressions you're going to get there, when you focus on it. And that lets you sort of like do better error checking, because now you have a kind of internal model of what you expect to see before you attend to it that you can compare to the low-level inputs and use that for further learning and error correction, and also directing the sensory organs around and other stuff, better forward simulation and so on. So this predictive interpretation, Jesse argues, and I also agree, has the best chance of unifying all the various effects attributed to attention. He says perceptual experience arises after a slight delay. In this brief instance, we get a kind of feedback loop. The first stimulus engages our ideational centers, and they generate a representation that serves as a template for us to resample the stimulus from the environment. And the idea is all the enhancing effects of attention and all the limitation effects of attention, all the selection effects of attention are effects and constraints on this forward model, right? This ideational model of what you're trying to anticipate seeing or hearing or whatever when you attend to the stimulus. And the same goes for intellectual attention, right? Like you form a forward model of what you expect to find when you consult your memory stores, and then you compare your actual memory to what you expected to find. And it also is related to solving these control problems that we talked about earlier, right? So Jesse in particular talks about having an overabundance of thoughts or perceptions. Just as we have a massively complex flow of sensory inputs, in both cases, the interesting thing is we manage to think about one thing in a more or less linear way, despite the fact that the mind contains an ocean of ideas, any one of which might be vying for current attention. And one of the solutions to this is to re-represent the selected line of thought. And so the thought is, just as this works for the human mind, if this is the right theory of human attention, this might also work for artificial systems. I'm going to skip over this. And, I don't want to skip that. So one of the nice things that, in particular in the context of the empiricism rationalism debate, is that James says we can't attend to something unless it has interest for us, and interest like drives the attentional mechanism in this fundamental way. And one of the things that's interesting in the context of the empiricism nativism debate is that innate differences in salience for interest can help us explain a lot of the things that nativists would think we need to appeal to innate ideas to explain, right? The idea being that, if you're a bat and you need to move by echolocation, well, you could have an innate idea of like echolocating space, or you could just build like a super powerful input mechanism for detecting echoes coming back from your echolocation mechanism, right? That's like an innate interest bias on the input side that will then lead through learning to greatly enhance sort of spatial acoustic learning, but without building in an innate idea is the idea. And so if we ask James, what stimuli do we think are innately interesting to humans? These are very general things, and things, pretty closely related to our sensory receptors, like moving things, bright things, pretty things, metallic things, words, blows, blood, et cetera, et cetera, et cetera. And so like, I would think like James would find, like Kiss and other hair bands or heavy metal bands, like very innately interesting. But the thought is you don't have like an innate idea of Kiss, right? It's just because they're like a salience assault on your senses, is the thought. There's a nice overview, again, by Grace Lindsay. I just can't recommend her work enough, about different approaches to attention in deep learning and how they relate to these mechanisms in psychology that I've been talking about so far. Let me see how I'm doing on time. Oh, geez, I've only got 10 minutes left. I'll say 15 minutes since we started a little bit after the hour. Let me skip over this. So let me talk about some of the ways that deep learning has been modeling attention already. And there's some simple ways, and then I really want to get to transformers, because this is the model of the attention is all you need family that's been behind GPT-3 and BERT, and if you've been following recent news, the PaLM model that Google just released, the maybe biggest deep learning model that we've got to date and by far the most impressive. They all work in virtue of an attention mechanism. So one way that you could implement an attention mechanism in a deep convolutional neural network type architecture, so like the cat labeling system that I talked about, about 20 slides ago, is you could build in a system for region proposal boxes. Okay, so this is like the system when it's trying to identify objects and images, it builds a limited set of hypotheses of places where you're likely to find objects, okay? And then it focuses extra resources on those areas, okay? So this for a while was the highest performing benchmark system, this faster RCNN on some of the benchmark tests. And you build a region proposal network that looks for like limited bits of the input stimulus that are especially likely to have an object in them. And then it directs additional processing resources at just those areas. Okay, so this might be kind of like ideational this might be kind of like organic adjustment, right? Where you're like looking at a particular part of the image that's especially likely to have good results. There's also another one that's even more like our visual saccades called the recurrent attention model that has what is called a glimpse sensor network, where it has increasing levels of visual acuity, just like our own eyes have kind of maximal visual acuity only in the center, and then less and less and less as you go further away from the center of foveation. And it has a recurrent network where the direction of this glimpse sensor on the stimulus is driven itself by learning, right? So the system learns to move this glimpse sensor around in an adaptive way as a result of solving tasks. And the idea is it learns which areas of a particular stimulus are likely to be most informative from previous training. So that's, again, kind of like organic adjustment, but now it's the mind's expectations that are sort of actually driving the glimpse sensor. So we're getting a little bit more sophisticated, maybe. Even more interesting, maybe this starts to get more like internal attention, is this system called the attention estimator network, which instead of driving around a sensor or a foveation type mechanism, it builds what's called a salience map. Okay, so the attention estimator tries to guess what are the most important aspects of a stimulus, and then it just like sort of adds weight to them in the final classification, right? So it's not that it's not processing the other parts of the stimulus because it's not in some sense looking at them. It's still looking at everything. It just like ups the importance of certain bits. And there's a network that, again, learns to do that in an adaptive way. And again, you got nice results, much more efficient and accurate processing by adding this attentional mechanism to the neural network. So you can already see there's a variety of ways that you add mechanisms explicitly inspired by attentional mechanisms in human psychology, and you get nice performance benefits out of them in the deep learning. Okay, so what about transformers? I'm not going to have time to fully explain them. It would take a 2-hour talk, unfortunately, to really explain how transformers work. But I'll try to give you the basics of them and some of the most impressive results that they've done recently. So transformers operate, you can think of it very quickly as a kind of this internally directed salience weighting, right? And they mostly focus, most of the examples I'm going to talk about, they work on linguistic inputs, right? So this is like GPT-3 that can generate whole bodies of text, just by trying to predict the next word one at a time. It can write articles that are, sort of passable as articles written by journalists. And in fact, that human raters can't reliably distinguish from articles written by humans. They're probably like B- B level undergraduate papers. At least, I hope that my students don't start, paying money to OpenAI to use GPT-3 to write their papers. But like, I don't know how we're going to stop this. It's that good already, and it's only going to get better. And they do it by weighting the input, right? So they have what are called these self-attention heads. and they build representations of the way that each term in a sequence is affected by all the other terms in the sequence, okay? And then they have multiple dimensions of that. So each word is going to have many, many attention heads representing its effect, the way that its meaning is in some sense colored by all the other words in the sequence. And each attention head can kind of specialize in doing a particular type of job. So it's easiest to give you just some examples. Again, I can't go through all this. But so once you get a trained up transformer, you can use visualization methods. So this is like, these links are shaded by the degree of weight that each attention head, so these are all different attention heads, different colors. And you can select just the blue attention head. And you can see that like when it's predicting the word, for example, that comes after slowly, it might more closely weight the turtle than the rabbit, for example. And that could just be on the basis of an association between the idea that rabbits are more likely to move quickly than they are to move slowly. But you can even get stuff that, I think I have an anaphor example up here in a minute. Yeah, so even cooler examples are where it looks like it's doing kind of like abstract. You have an attention head that looks like it's kind of specialized to solve a kind of abstract rule resolution type thing, like anaphor resolution. So suppose you have the sentence, a robot must obey the orders given to it, right? Good Asimov reference. When you get to it, right, the system needs to understand that this is an anaphoric reference to the robot, right? And in fact, you find an attention head in some of these trained up examples that looks like it's placing special weight on a robot when it's trying to understand the meaning of it. And so the idea is it's sort of resolving that when it's building its representation of the word its meaning in this particular context. And then it uses that weighted representation, which is in some sense looks like it's resolving the anaphor, to make all of the downstream future predictions for what text should follow then, right? So if you're talking, if it is the robot, that's going to change like what you're talking about in the next sentence and what adjectives you use and so on. And this is just one example. There's like, it looks like there's attention heads that are kind of specialized to do all kinds of different things that we would think of as being like syntactic, semantic, and even sort of blend of syntactic and semantic roles. And they're using attention mechanisms to do it. Goyal and Bengio even say in this kind of recent review paper that this attentional mechanism transforms neural networks from machines that are processing vectors to machines that are processing sets, more particularly sets of key value pairs. And they say this implements a form of variable binding, right? So something that neural networks all along in the old critiques from the 80s and 90s were supposed to have a very hard time doing or require very specialized mechanisms to do. This might be why attentional mechanisms work so well. There's also cool examples like with music transformers. So it's not just predicting words. You can use it to sort of predict any sequentially structured input. Like it can generate very interesting music. If you Google music transformers and listen to some of the creations, you'll probably be wowed if you've never looked at this stuff yet. But if you look at a particular position and look at different attention heads, it looks like some are attending to the melody and some are attending to the harmony and some are attending to chord progression and other stuff that looks musically meaningful. And again, none of this is innate. It's all just programmed in. It learns to do this all from the training set. Now, I have to mention Palm, just because this only came out a couple weeks ago. This is the biggest deep neural network transformer model to date that's been released. It's 540 billion parameter model. So it's approaching the complexity of a simple brain, you might think. And an attempt to understand how much progress has been made in the rapid transformer development over the last couple of years was this Big Bench project. And they put together like 160 different tasks. A reading group I'm in actually contributed one on novel concept combination. But a lot of these are things like word arithmetic problems, joke explanation, causal understanding, logical inference, things that deep learning and neural nets in general were all supposed to be very bad at. And this blue line is all the cases where Palm outperforms average humans. Okay, so on a majority of tasks, it's at least doing as well as, and in many cases better than humans on these tasks that it was supposed to be very, very bad at. We're supposed to still be, 20 years away in the future. It looks like it was just a matter of scale. So there's lots of cool results here I could talk about more in the Q&A, but they're sort of related to attention in an interesting way. So word problems, these are the kind of problems my 9-year-old is solving, in elementary school right now. These were things that deep neural networks up until now were just terrible at. But they found if you do what they call chain of thought prompting, which is where you add the kinds of scaffolding hints that you might give a child when they just first start doing these problems. Like, so the pink part here is the chain of thought prompting. You say, Roger started with 5 balls, 2 cans of 3 tennis balls. Sorry, I can't read that. This is my Windows. Is 6 tennis balls, 5 + 6 = 11. And then it still gets the right answer. But what's even cooler is that on the next problem, it can do its own chain of thought prompting. So it now generated everything in the pink here in the later model output and provided its own chain of thought prompting that now let it get the right answer on the next word problem. Okay, so like by you guiding, you might say, its attention with these chain of thought prompts on one problem or a couple problems, it later learns, you might say, to guide its own attention by itself generating more chain of thought prompts, which maybe is kind of like how kids do it. There's also counterfactuals that are super cool. Again, this is supposed to be something that neural networks couldn't do. They can explain jokes in an interesting way, even jokes about machine learning. I'm now in the last 5 minutes or so. Do I have 5 minutes at least? Yeah, I'll say I have 5 minutes if we started late. So if you've seen any LeCun talk in the last couple of years, he thinks that the future is this self-supervised learning that's explicitly predictive. And so the thought might be that now with everything we've done with transformers and generative models like GANs, we can now go to the next step where we're actually building a forward model that the model compares to its own actual later observed input and use that to guide its own learning. So instead of having to train these models using these huge supervised data sets like ImageNet, we can now have the network learn from its own anticipated observations and then error corrections. And so these generative models like transformers might be able to implement this next step, which is kind of doing the final leap to full Jamesian ideational preparation, okay? Which would then have all the other downstream effects that we mentioned earlier from the forward modeling having like limited resources and enhancing processing and so on in a kind of a chain of prompt type way. I can't explain GANs. But if you look at what some of these generative models are doing, I can just kind of wow you with a few pictures at the end of the talk. These were, so these are people that don't exist, generated by this tool. These people don't exist. And you can imagine, this is how high resolution some of the forward models could be that you then compare to actual observed inputs. We already have the power to generate some of these perceptually realistic stimuli. And Gershman has a paper, if you follow any of his work at Harvard, on the potential for this type of idea being applied to understand the relationship between machine learning and human psychology. So I love this model, but there's not time to explain it. Ask me in the Q&A. So the next steps, the idea in machine learning is we will use all this generative power to guide the processing of a complex DNN architecture with multiple faculty modules, much like James suggested. Generative modules can be used to create advanced simulations of what the system expects to find after performing some active perception or memory recall. The takeaways here are empiricists, whether philosophical or machine learning, should get active domain general faculties. In fact, that's how both the recent advances in machine learning and the philosophical explanations in Hume and Locke all work, basically, is by appealing to faculties. And empiricist DNN researchers should start thinking more systematically about solving these control problems that will face richer, more coherent cognitive architectures. By the way, a bunch of empiricist philosophers have already thought long and hard about this, so you might learn something if you go back to the history. And we're now poised for this approach to using generative models for self-supervised learning, explicitly modeling aspects of attention and brains to unlock the next breakthroughs. So thank you. Sorry to come up so close to time.
Thank you, Cameron. Actually, you have 5 more minutes, but I should have let you know earlier. But again,
go back to the model that I skipped over because it's super cool. It's like my favorite model. Maybe in the Q&A. Let's see where it goes.
Okay, yeah. But thanks again for this very exciting talk. and I believe the audience has come up with many questions. But let me remind everyone that the instruction for Q&A is posted in the chat, and I will open it up for posting the question after the commentary. So our commentator today is Professor Amit Chaturvedi. Amit is assistant professor of philosophy at HKU, and he works at the intersection of Indian philosophy and philosophy of mind. Most of his research focuses on consciousness, attention, and perceptual expertise. So let's welcome Professor Amit Chaturvedi.
Thank you, Linus, and thank you, Cameron, for a really amazing and stimulating talk. And I've benefited a lot from reading your chapters and hearing your presentation. And so I can't hope to respond to or capture all of the rich detail of Cameron's presentation. Instead, I wanted to sort of use Cameron's talk as a bit of a springboard, well, use it as a bit of springboard to talk about my own research, not just for self-interested reasons, but also as a way of sort of building on this general theme of Cameron's book project about how the history of philosophy can inform contemporary debates in the philosophy of mind. And so I wanted, and specifically how theories of empiricist psychology can help with, current debates in artificial intelligence and philosophy of mind. I wanted to talk about some relevant ideas from classical Indian Buddhist empiricism, and specifically having to do with the notion of the self and its origins. How Buddhist empiricists account for the origins of our self concept, as well as all other concepts through the activity of attention, or interestingly, in some ways, inattention and ignorance. And the reason this is interesting, the reason I think it's worth bringing up in the context of Cameron's talk is, for one, if we think about what's the motivation of all this work in developing deep neural networks that model or simulate how the human mind works. Well, one central aspect of the human mind, perhaps, is the notion of self. For Buddhists especially, it's particularly pervasive throughout all of our experience and motivating all of our, driving all of our thoughts, motivating all of our actions at some basic level. So it might be useful to consider their account of the self within a broader empiricist framework that is consistent, I think, with a lot of the classical empiricists that Cameron is drawing on. And again, part of what strikes me about the brilliance of Cameron's project is how it illustrates the value of doing history of philosophy, as Cameron said throughout his talk. For one, thinking about the history of philosophy as presenting live options in contemporary debates, one that helps us to understand or reframe classical debates, like the central one in Cameron's project, that between empiricism and rationalism, in a new light, and his distinction between domain-specific versus domain-general knowledge and representations. That's been helpful to me in reframing what this classical debate was all about. And at the same time, as Cameron also says, if we go back to the history of philosophy, we can also continue to mine gems, new arguments, new insights, new concepts that can inform and reshape contemporary debate. So what I'll try to do now is look to another possible treasury of empiricist gems, and that it can be found in the thought of the 6th to 7th century Indian Buddhist philosopher Dharmakirti. And I'm going to just give a very quick overview of why he should be called an empiricist. Dharmakirti postulated that there are two sources of knowledge: perception and inference. And he thinks that perception is the foundation of all knowledge within his philosophy or his epistemology, and really for pretty much all of classical Indian epistemology. There's no real significance given to or epistemic role for a priori reasoning. Perception is always taken to be the sort of foundational source of knowledge in most any classical Indian school of epistemology. And the reason he thinks that perception is especially the fundamental source of knowledge is his prior commitments, or metaphysical commitments, to a kind of trope ontology and nominalism, and that should strike you as bearing a family resemblance with other classical British empiricists. Dharmakirti thinks that persisting and composite substances, abstract and shareable properties, as well as objective similarities, these are all unreal entities. And so instead, what we have to work with, like how we build up our knowledge of reality, well, what is reality? First and foremost, for him, it's a composite of, not a real composite, but yeah, it's sort of, you can think of it as a kind of array of what he thinks of as unique, propertyless, momentary, and partless particulars, like unique particulars, basically, that all exist for one moment, that are all causally efficacious, but they are simple and that's what's fundamentally real. I think it's helpful as a metaphor to think about reality for Dharmakirti as being a kind of array of sensory qualities or tropes, and that idea, I think, is has resonance with how it is that deep neural networks, like say a object recognition network, has to start with an array of pixels, of visual pixels, and from this array of visual pixels carve out patterns of meaning and significance and abstraction. And so the question is, well, how does Dharmakirti think the human mind does that kind of carving out? Well, again, so perception has a different function entirely, because it represents entirely different objects than that of conceptualization or inference. Perception serves to vividly represent causally proximate particulars. Again, this notion of vivacity or phenomenal vivacity you can find, I think, in Hume quite clearly. Conceptual awareness or inference more broadly, that functions to non-vividly represent abstract categories through propositional and predicative judgments, linguistically expressible judgments. Perception is fundamentally linguistically inexpressible, or the contents of perception, that is. So here's a kind of engineering problem that arises for Dharmakirti's account of the mind. How do we bridge the gap between perception and conceptual categorization? How do we actually identify unique particulars as being the same, right? If every entity in reality is fundamentally unique, utterly distinct from anything else, how is it that we ever go about cognizing anything as being one and the same thing? I see that, like, as it turns out, this water bottle, when I see it, the moment I see it, this water bottle is entirely a new thing by the time I reach out and grab it and drink from it. Why does that not reflect, how are we able to overlook that fact about reality? And this idea of overlooking indeed is really central to Dharmakirti's account of concept formation and acquisition. Basically, he thinks that we are able to identify unique particulars as being the same and conceptualize them as such by fundamentally ignoring or not attending to the unique particularities or differences between, for one, a presently perceived object and the previously experienced objects that this present object is taken to resemble, not objectively, but subjectively. And then we also have to overlook the fact that we are presented in Dharmakirti's mind, in our minds, with a mental image. So we have this mental image in our awareness that resembles somehow an object outside of the mind. That's what we're fundamentally acquainted with. We have to overlook the fact that we're only acquainted with an internal mental image and conflate that with, or ignore the differences between that mental image and the external object that we take ourselves to be in contact with and interacting with through our perception. So fundamentally, since Cameron's talk has been centered on the notion of attention, I think there's a interesting sort of counterpoint in Dharmakirti, counterpoint to classical empiricist accounts of attention and abstraction of concepts from sensory experience. Dharmakirti suggests in some ways that inattention is as much, if not more, central to concept formation and abstraction. And again, this idea that we base our abstractions on a resemblance between particulars, mental images, and objects. Again, these are subjective, not objective resemblances. So it has to do with not anything about, not how the world objectively, particulars in the world objectively resemble each other, but how they strike our mind as being similar. And the resemblance for Dharmakirti that's most fundamental is that particulars will be grouped together as identical or as being of the same type if they all similarly cause a judgment, some judgment, namely this is X. Basically, objects are similar to the extent that they cause me to think they're similar. So for instance, let's say you have 3 utterly unique cookies, And for each of these entities, we form the judgment, very commonsensically, this is a cookie, right? Now, this is a cookie is a conceptual judgment that is ultimately a fiction and fabrication of reality, but it helps us get by, helps us satisfy our hunger, not by tracking any objectively existent or shared property of cookiehood, but rather by this judgment helps us interact with the world through this process of ignoring every particular object or mental image that doesn't cause the judgment. This is a cookie, right? So again, we're not tracking anything objectively or positively in reality. We are instead just ignoring all those things that don't cause us to think this is a cookie. And that for Dharmakirti is sufficient and ultimately, yeah, the basis for conceptual abstraction. And the reason we ignore all these other things that don't cause this judgment in us, because they don't satisfy our pragmatic interest, as Cameron talked about, this notion of interest as being central to how we attend. Interests for Dharmakirti as well are the foundation for our conceptual judgments and for our patterns of attention and inattention towards the world. If these things don't satisfy our pragmatic cookie-related interests and desires, then we won't classify them as cookies, but not because they have or lack any objective cookiehood. And so basically the broader question that Dharmakirti is addressing is this: if we never experience sameness and yet experience as an empiricist, you'll have to say experience is the basis of all mental contents, how do we ever acquire the concept of sameness and think that two things are the same thing? Again, we've seen there's a kind of ignorance at play. Dharmakirti actually talks about this beginningless ignorance, because again, we could never have acquired the concept of sameness through our interaction with the world, because nothing in the world is actually the same. So he thinks that it takes a kind of beginningless ignorance, this innate tendency to that belongs to all sentient beings, not just adult humans or humans in general, but all sentient beings have this innate disposition to equate different things as identical or differentiate unitary things into multiple things, distinct things. And this is sort of the foundation of Dharmakirti's account of concept acquisition. This is all he needs as an empiricist to get the process of concept abstraction off the ground. And to that extent, I think it's revealing for in the way Cameron's rephrased the debate, to think of this tendency or disposition as innate, but yet domain general, as pervasive throughout all experience and thought. And related now coming, I'll just take a few more minutes if you don't mind. A related question that Dharmakirti actually relates to the first question about sameness and how we build out the notion of sameness from experience of a world in which nothing is ever really the same. Similarly, Buddhists will have to deal with this question. If reality is, according to Buddhists, is selfless, i.e. we never experience the self, like Hume said as well, and yet experience is the basis of all mental contents, how would we ever acquire a concept of selfhood, and thereby think of things as being me or mine? And again, Dharmakirti will point to invoke this notion of beginningless ignorance, i.e. an innate disposition to identify unique and momentary entities as being or belonging to a self. And again, this is definitely innate. It's an interesting question as to whether it's also domain general. Cameron has raised objections against certain contemporary rationalist accounts of innate concepts, like the concept of object or concept of self or agent. These rationalists think that these are innate and domain specific. I wonder if we could perhaps think of the notion of self in this context, right, in the Buddhist context, as being domain general, just because it's so pervasive and underlying all representations of a world, all interactions with the world as being other than me, or as being external to me, and yet somehow being able to be possessed by me, and so on. So perhaps it could be also domain general, at least in that way, consistent with a broader empiricist orientation. And very, very briefly, other Yogacara Buddhists also talk about attention's role in setting up a distinction, creating a distinction between subject and object within the mind. For these other Buddhists, they think that this distinction, this subject-object duality, is created by the activity of discursive, what they call discursive attention, which is basically attention as conditioned by inner speech. How this is supposed to work, or what this is supposed to amount to, is basically these Buddhists think there's this linguistic or cognitive act of selection, both selection as well as what you might think of as the repeated fixated ideation on and classification of mental states as being self or other, subjective or objective. And again, because the world isn't actually doesn't actually contain a ultimately real, fundamentally real subject-object duality, this has to be created by the mind, and it can't be learned in a way by the mind. It has to originate from some innate, you might say, interest bias or innate inductive bias that the mind is born with. But perhaps that can still be consistent with an empiricist orientation again, and also perhaps it can also be modeled in artificial systems, right? So I just, this is one paper among many. Elaine Morin is someone who's written a lot about inner speech and its relation to self-awareness. Now we can start to think about, well, if the self is so integral to our experience, it sort of underlies our basic interactions with the world and conceptual thought more broadly, then, insofar as artificial intelligence is trying to simulate the human mind, well, how might it simulate or thereby genuinely acquire a notion of self? And what role does something like attention and or inner speech have to play in that process? So I'll just now end with some broader questions for Cameron to use as stepping stones to talk more about his project or what he might see the relevance of, say, Buddhist empiricism and its theory of self-concept or self-conceptualization. How might that be relevant to his broader project of understanding the relation between empiricist theories of mind and developments in artificial intelligence? So here's one very broad question. How should empiricists explain the acquisition of a self-concept? It's unclear. I mean, I haven't read the classical British empiricists very closely very recently, but I'm not sure they have a very clear account of how it is we acquire a notion of a self. Hume says we never experience a self, but then why do we think of a self in the first place? And is the self-concept an innate interest bias, as some Buddhists might suggest? Another question is when and where, or when would and should say an unsupervised or self-learning deep neural network begin to distinguish between self and other? Why should it in the first place? What sort of environmental conditions, if it's solely learning from its environment with no prior innate pre-programmed representational knowledge or structures, would a deep neural network ever come to distinguish between itself and its environment? What effects might that have on its processing more broadly? Would that be advantageous or in some ways disadvantageous? These are all just broad questions for Cameron to run with. And then finally, how might self-awareness in either human or artificial agents be tied to or grounded upon the activity of attention and attentional agency? So these are just some questions that arose for me in response to Cameron's talk, and I very much look forward to Cameron's response in turn. So thank you all for the time.
Thanks, Amit, for this very insightful comment. So before we invite Cameron back for a response, I want to say that the chat room is now open for questions. So please follow instruction there to post your questions. And Cameron, the floor is yours.
Yeah, so thanks so much, Amit. That's exactly the kind of information I was hoping to learn from your commentary. And I hope to get a long reading list from you later too. I'm struck, maybe as you are too, by the kind of echoes. You always want to be careful when you're jumping between traditions, but it seems like there's a lot of similarities between the types of problems that Locke and Hume, or even later empiricists like James and Quine, were worried about, and the concerns and problems that you just described, especially, like skepticism about the self in Hume, or skepticism about principle of similarity in Quine. I think other people have noted this relationship before, but I think it's also really interesting. I wish I could write another chapter in the book, but I'm already in late stages of revising, so probably my editor's going to say don't do that. How to build systems that can develop a concept of the self or a sense of the self from an empiricist perspective, and whether you need a domain-specific interest bias, I think is fantastic question to be asking. And in the next chapter after the attention chapter, I focus especially on social and moral cognition, and in particular the empiricist views of Adam Smith and Sophie de Grouchy, who try to tackle exactly this question in their work, in particular with the faculty of sympathy. And I like Sophie de Grouchy's work in particular here. It's more useful for moral psychology type questions than maybe the philosophy of mind type questions that you focused on. But she was really interested in this sort of an ethics question of like solipsism, like egoistic solipsism versus moral regard for others. And her solution was kind of unique as an elaboration of Smith's, and that she thought that she emphasized like the earliest experiences in infancy and the kind of reciprocal interactions that an infant has with its first caregivers. And the cool thing there was her argument was like the infant at that stage doesn't yet have a concept of self, right? They don't have a self concept as being different from the caregiver or others. But they nevertheless learn that their cries can influence the caregiver, and the caregiver's distresses or joys are directly relevant to them getting positive reinforcement or negative reinforcement. And so they start caring about others and learning to pick up on and read other people's emotional reactions before they even have the cognitive capacities to develop that self-concept for themselves. And that kind of like solves this self-other value gap before it even emerges. And I've in that chapter, I also look a bit. So like, if, you get into the developmental psychologists, they think that the self-concept emerges like in a series of stages. This goes back all the way to Piaget and has been elaborated in more detail by sort of developmental constructivist psychologists and sort of offer some guidance from that perspective to the roboticists about how you might get there. I'm not sure I have a firm answer yet on whether it requires a domain-specific interest bias, but I can sort of speculate as to how the answering that question would go, right? So the empiricists would hope that there would just be certain correspondences, I guess, between like volition and proprioception and sounds and vision coming together in a certain correspondence, abstract correspondences, like you might think in a kind of topographical sense, and that would be sufficient to think that like there's a particular perspective on things associated with a particular body, just as a result of kind of domain general abstraction, the same types of abstraction mechanisms that operate in other domains. When you have these correspondences that come just as a result of like the sensory organs and proprioception and internal mental actions all being coordinated in a certain way, that there's no necessary innate idea that you have to add on top of this other domain general bias to like ignore stuff that's not relevant and focus on stuff that is relevant that you talked about in your commentary. That would be the hope. I mean, of course, the proof is in the pudding. You got to build a system that can do it without having to build in a domain-specific bias before it would be really convincing, but that would be the project, I think. So I might, mention that. I still have some chance to revise the chapter. It would be a fun problem to set up for the roboticists. Do we want to go to other questions?
So thanks, Cameron. We are running a little bit late, so we will have the open Q&A after we kind of formally ends the seminar. So let me just formally thank Cameron for this wonderful presentation and Amit for being an equally wonderful commentator. And on behalf of the Society Fellow, Philosophy Department, and AI Humanities Lab, I would like to thank everyone for your participation. And we'll carry on the open Q&A informally after this, but please feel free to leave if you have to go. So the first question goes to Herman. So Herman, you could, yeah, thank you.
Hey, can you hear me?
Yes.
Yeah, I can.
Yeah, okay, good, thanks. That was really, really interesting. I guess I'm still trying to get my mind around just how ideational preparation kind of ties all the cases in the second part together. So I'm not getting a full grip on how it's a unified phenomenon. I think I kind of understand it for picture classifications, like the first example with the truck and that slide. But it's just less clear when you go to things like, a deep neural net classifying people as creditworthy or at high risk for recidivism or qualified for a certain job or something. And I also didn't quite see how the picture cases worked in the same way as the multi-head transformers in GPT-3, like where you got the weighted representations helping you to get it be anaphoric on robot, for example. Like, how was that ideational preparation in the way that it was in the picture classification one? And yeah, I had kind of the same things about the Google 540B transformers and so on. So just, this is just, clarificatory to some extent. Just help me see how all those cases kind of get tied together.
Yeah, so some of the simple examples that you talked about in the beginning, like classifying applicants to a job or predicting recidivism, like, maybe you're thinking about like the compass algorithm, that probably isn't even deep learning. It's probably a simple kind of, there's not that many variables that you need to sort through. And none of them involve a forward simulation attentional mechanism, like the kind of ideational preparation that I would think will be involved in models that can really do this. So they're missing the whole attentional mechanism that I think the next generation of models will want to have if they're building something in that's going to solve these control problems in the way that James thinks they should. So what is that mechanism going to look like? This sort of gives me an excuse to go back to that model that I skipped over at the last bit. Can I go back to my slides? Because it's going to be impossible to explain without the picture.
Sure.
Let me try to do that quickly. So the short answer.
So right now you're not sharing the screen. So
yeah, I know I'm doing my screen.
Okay.
Well, I think maybe you see my storm there.
That's your kids.
Do you see my slides now?
Yes.
Okay, so this is the model I want to talk about. Okay, so the idea is like Compass and the other, like the job predicting model, they don't have this, but here's what a system that had this would look like. The thing that I'm picturing, right, is we add like an additional module to these systems. That's the ideational preparational module. How does it enhance processing? How does it provide all these sort of like selective limitation effects? It's because it has limited resources. And what it's doing is it's like picking some aspect of the stimulus or internal mental operations like memory retrieval or whatever to forward simulate. And it can only forward simulate one thing at a time. Now, the thought is this would be a generative model like the people don't exist and transformer type GANs that we talked about earlier. Now, the part that I completely skipped over, but I desperately wanted to talk about, is this same trick of using GANs to build long sequences of text, like documents like GPT-3 does, can be used for other types of stimulus type input too, like sound or image, okay? By treating them as like a 2D or 3D array of sequenced abstract features. So this is a system that puts like all three types of neural network architectures that are really popular today together in one super architecture that can sort of do everything. So you have like a deep convolutional neural network that discovers what they call a code book of abstract features. So, if it's building pictures of dogs, it might have like an abstract feature for nose and an abstract feature for dog eye and an abstract feature for dog ear and hair and so on, right? That's just to give it kind of like a limited code book. Then you pass the input image to a convolutional neural network encoder that basically says like, what abstract features did I find in that picture and where did I find them? You can then pass that codebook annotated representation of the image to a transformer. And the transformer learns long distance relationships between those features, like the way that the image is visually composed, right? So it learns that the nose stands in certain long distance relations to the ears and the eyes and so on, right? So it not just has a representation of the abstract features and where they're located, but also the long distance relationships between them, as if they were like, grammatically structured words in a sequence. You can then pass that representation, the sequence annotated abstract feature representation, this is called the quantized like array representation. to a generative model that will then build it into a new picture of members of that category. Now, the cool thing about this is you can associate words with elements of the code book that can have the long distance relationships between each other annotated by the transformer. And so you don't even have an input picture to start with, you rather have a text prompt. This is basically how like DALL-E and DALL-E 2 work, if you've been following that on Twitter. If you don't know what I'm talking about, immediately after this question, go on Twitter and look up DALL-E 2 and look at all the cool stuff that you can build from nothing but a text prompt. Okay, so you pass this quantized transformer modified representation of the text prompt to the generative model now, and it can generate a plausible picture of, you know, almost anything you want on the basis of the compositional relations in the text prompt corresponding to compositional relations in the image. So later here, I have some examples of this I did from Hume. So some examples that Hume gives of novel ideas that the mind can create. He says, winged horses, fiery dragons, and monstrous giants. And, you know, I passed this text prompt to this generative model and it built this, right? Which is cool. Not nearly as good as what DALL-E 2 can do. I gave another example he gives is the New Jerusalem with streets of gold and walls of gemstones. And it gave this, like you can make out a temple, you can see the gold is inlaid between cobblestones. It's like, it's pretty cool. I used to use this example when I was teaching Fodor on the productivity of the human mind, right? Imagine a tiny pink elephant in a tutu holding an umbrella and hanging from the ceiling in the back of a classroom while singing a sea shanty. And, you know, you can all imagine what that would look like, even though you maybe never thought about that combination of properties before, and it does it pretty good. I'm sure DALL-E 2 would do like way better than this. This is me fooling around 15 minutes on a laptop with a Google Colab notebook. That's how powerful this stuff is. So how do we get all those constraining effects and all the different downstream process enhancing effects, right, to kind of summarize how this type of architecture, if you added it as an ideational preparation module to other systems? Well, imagine now that, you know, even like Amit was talking about the role of inner speech for the Buddhists and developmental psychologists. Imagine that you've got this like train of inner speech that's expecting what you're going to find as a result of doing some action or perception or whatever. And then the ideational preparational generative module is building a forward model of what that's going to look like. Like the, you know, like you think of kind of imagination imagery that happens in imagination while you're going through a train of thought. Then you can compare what you see to the forward picture expectation that you had, and that like enhances your processing and limits what you're able to focus on and the comparisons that you're able to draw in this way. So that's the way it kind of like brings everything together by adding an additional ideational preparational module onto the cognitive architecture. This is all pie in the sky stuff, but look, I'm a philosopher, I'm a very speculative one at that. But these are all the bits are already there. Is what I'm saying. And nobody's yet taken the leap to actually put them to the kind of functional use that James suggests that they should be put if we're going to model the human mind. That was a long answer, but I hope it was sort of cool.
Thanks. So the next is Giorgio.
Well, yeah, thank you, Cameron, for this rich, extremely rich talk. Well, actually, I don't mind being seen. I'm just wondering, there's one area of in the history of psychology that wasn't touched on, and that's cognitive psychology, the idea of schema. So I'm wondering whether James's ideational preparation has anything to do with what Bartlett and then, of course, the cognitive psychologists refer to as a schema. And I'm also reminded here of Bartlett's famous pronouncement that perception, talking about, you know, blending faculties or the confusion between one faculty and or the overlap between faculties or across faculties. Bartlett said the perception, much of what passes as perception, if I remember correctly, says is in the wide sense of the term recall. And so, you know, they don't seem worried by that at all. The cognitive psychologists, by the, you know, but in general, faculty psychology became discredited, I think, you know, in the 20th century. So it's interesting that it's being revived via engineering. But my question, more to the point, has to do with, yeah, precisely whether attention is a disposition rather than a faculty. and whether that change, after absorption, for instance, which is also a disposition, I would say. And related to this, you said that James talks about distraction as the opposite of attention, but attention needs a foil as distinct from an opposite, and that foil is inattentiveness. And the chapter on attention really begins with the fact that there's too much for us to attend to. Hence, so how does inattentiveness factor into the models that engineers are model, if at all? Or don't they need inattentiveness because they're working with very limited lab, with images that basically are, presented to a deep learning machine without any potential distraction. So I'm just curious about this broader picture.
Gosh, I mean, there were 4 or 5 questions that I wanted to answer in there, and I've already forgotten the first 3, maybe because it's late here. But I'll try and try and answer the last one.
Yeah.
I mean, one thing I do say in the chapter is, and I think James is vulnerable to this too, is that he tends to emphasize sort of the positive aspects of directed attention and volitional attention, and then like be really negative about lack of attention or distraction or what we now call mind wandering. And that's one tendency that I do try to push against in my chapter. In particular, at the end, there's a lot of great work, like I think, Jess Whittlestone and Zach Irving do cool stuff on the functional significance of mind wandering today. So I do want to push back on that a little bit. I do remember one of the other things that I was going to say. So the first bit about schemas in the beginning. I do think that that the ideational preparation aspects, if you implement it in kind of the way that I was just suggesting, will be scratching the same itch. There was, of course, in AI a lot of attempt to model sort of schema type application, but in the good old-fashioned AI, right, the rules and logic-based AI, and where you had a series of sort of like very structured logical expectations of what's supposed to happen in the schema, and that was driving the type of processing. And that was sort of like brittle, maybe in ways that you wouldn't want it to be, and you have to worry about symbol grounding problems and stuff like that. But the hope would be today that there's now a lot more under the hood, kind of very structured probabilistic expectations driven by very intricate, subtle correlations in the training set that could do the same type of operation that the psychologists study as a schema, but now in a much more flexible and kind of deep, rich, and hierarchically structured way. So the hope would be you're doing, and I think like Goyal and Bengio, maybe in that review paper I cited, they even explicitly draw some of those links to the old schema stuff, if I'm remembering correctly.
And also to echoing a bit Herman's concern that vision is more than just recognition. So the examples you presented are mostly of recognizing things by basic, but of course to look at something is much more than that. So I'm wondering whether people are also playing with other aspects of vision, aspects other than recognizing something.
Which aspects did you have in mind? I mean, if we did the ideational preparation, then we would be doing a little bit more than that. We'd also be kind of like forward modeling, but I'm not sure which aspects you had in mind.
Well, vision as in exploration across time. So sort of continue.
Yeah, so some of the models, like where you have the glimpse sensor that it learns to direct around, that might get at some of that, or the object proposal boxes where you're directing more resources at particular subsets of the image. I think the glimpse sensor one sort of like explicitly tries to model some of the exploratory aspects of attention, because the idea is that what the system's supposed to learn how to do is recognize like sort of like where it's more uncertain and what is likeliest to be the part of the stimulus that's going to provide more information and direct further the next stage of processing there. So I don't know if that gets exactly what you're after, but maybe at least
it does. I was also thinking about, of course, the way in which looking at something is shot through with emotional.
Yeah.
Right.
So I talk about that in the last chapter too, a lot about the role of affect and how we're really in kind of the dark ages of modeling affect. There is this whole area called effective computing, but they're mostly trying to get machines that can read human affect and respond correctly to human affect, to have like good robot caregivers and stuff like that. Whereas, you know, what you'd really want to see is, I talk about this explicitly in that last chapter, is robots that are modeling the various, you know, what Hume would call passions, that have like affective content. That plays a huge role in Adam Smith and Sophie de Grouchy's moral and social psychology, and lots of aspects of Hume's psychology. And we're just not really trying to model that stuff yet. But there are reasons to think like, would they be really hard engineering problems? Because you think you probably have to have a body to get it right. Right. That's the part where I think, like, you know, nativists often think that like empiricists don't think evolution is important to getting the mind right, and that's nonsense. Of course, like every empiricist think evolution is important. The question is like, where do you think evolution expresses its really intricate influence? And empiricists tend to think like the body is way more important to cognition than we think. So it's not by packing innate representations into the mind. It's rather by shaping the body to create certain passions in just the appropriate sorts of circumstances that they can influence learning, and particularly you might think reinforcement learning in the right ways.
Christopher, please.
Yes, thanks for the great talk. Something we find with these huge models, like these language models you have mentioned, is that they have this capacity of few shots learning, which means that they can, for instance, they have learned to classify 1,000 or 10,000 different animals, and then with a few examples, they can learn to categorize 2 new animals. And I just wonder whether this can be related to your ideas about attention and ideational preparation. Does it offer like additional insight, especially given that there is somehow a quantitative component here? Like the more knowledge you can learn first, the better few shots learning seems to work.
Yeah.
Thank you.
Yeah, fantastic question. I don't want to oversell our current understanding. This is like, I think we still don't exactly know how these systems work. I've been following really closely the work of Chris Olah. He started a new startup recently called Anthropic AI, I think. And he's released a couple of papers/blog posts recently where he tries to really unpack what transformers are doing, and in particular in a few shot learning type situation. And the thought is, that what's happening is there's a kind of fuzzy rule application where the context that's provided by the prompts sort of helps the system determine. Olah calls these induction heads. So the attention heads get kind of transformed into this fuzzy match induction rule type mechanism, where it kind of scans through the abstract representation it's derived of the training history through one layer of the attention head, to find some sort of like area of the space that's roughly similar. And then it does a kind of like modified fuzzy copying from that previous experience. So it's not just like literally copying a sequence in a lot of these cases, but it's sort of like adapting the rule that it's acquired from its previous experience to the present case in the way that's appropriate to the recent context. It's very hard to explain without getting into the details, but if you look at Chris Olah's recent work, you'll see something to that effect. And it is the attentional mechanism that I described in transformers that's allowing them to do that, right? So the attentional is just a way of like weighting certain areas of its representation space more highly than others, and in virtue of the recent context. So that's how the few shot learning works, right? Is it's the weighting which aspects of the recent context should be like accessing which induction rule to look up to apply to make the next predictions. Now, there's nothing yet there that's really like doing the full ideational preparation thing that I was suggesting at the end of the talk. That was a forward thing to do later on. There's no like forward modeling. It's just trying to predict the next word in the sequence. I mean, at least as far as we know, right? So like the Palm model that I talked about, I think it's got something like 118 layers to each of its attention heads, which is, you know, we have a hard time understanding a 2 or 3 layer attention head architecture at this point. So who knows what's happening in those 118 layers? I hesitate to even speculate, and we definitely don't have a mechanistic understanding of it. It seems entirely possible to me that it could be doing some much richer forward simulation than we think. So I don't know. But until we really understand how these systems are doing these crazy things that they weren't supposed to be able to do, it's hard to give any answer with much confidence.
Rachel, please.
Hi there, thanks so much for your great talk. I just had a question. So I've been sort of interested in the sort of development of the attention literature that has to do with like normative demands on attention. And I was wondering like how you might account for tasks that are going to require these more normative demands on attention. So this is sort of a follow-up on Herman and Giorgio's comments. So I'm thinking even in some cases, categorization is going to require, you know, that we should pay attention to something or not pay attention to something. And even in doing predictive modeling, it could be the case that you have these sort of normative demands. And I was wondering if you know, your current model of ideational preparation can accommodate this or eventually accommodate this aspect.
Yeah, cool question. You probably mean normative demands in a more generic sense, but some of this does come up in the things I say about moral cognition in the last chapter. So one of the things that like Adam Smith and Sophie de Grouchy spend a lot of time worrying about is how do we develop a more impartial perspective in moral and social cognition. And Smith's theory kind of famously is that we learn by acting in certain situations that our peers or superiors, you know, like teachers and other authority figures, are going to approve of certain ways that we do things and certain things that we attend to, and disapprove of others. There's a kind of famous take on Smith's view that we achieve a kind of like impartial observer perspective, specifically by learning how to modify attention in a way that answers to some of these normative demands that we've learned on the basis of previous patterns of other people sort of lauding us or criticizing us or even comparing ourselves to their performance, so that we try to like not get criticized or get lauded in advance of explicit feedback, to focus on just the aspects of something that in some sense like we think an impartial observer should. And probably, you know, that basic story might work for even some of these categorization examples that you want to talk about if they work in the moral realm, right? Where you learn like you shouldn't attend to, you know, very particular idiosyncratic aspects of your personal attachment to something when you're making a decision in a sort of justice or fairness context. And that can be understood as a way of modulating attention in a way that impartial observers would agree with if it were subjected to scrutiny. So that, you know, that would be my general strategy, where that impartial observer perspective is something that is itself learned from feedback from previous performance.
Okay, thank you.
Okay, so it's almost 11 in Houston, so we should let Cameron go get some rest. So again, I want to thank Cameron for joining us, and also thank everyone for this great discussion. And I look forward to seeing you again at the Society's next lecture. And bye for now. Thanks, everyone.
Thanks, Linus, and thanks again.
Thank you. Thanks again for the invitation, and Amit for the commentary.
Thank you.
Bye.
Good night.